Welcome to the second part of the discussion on the analysis of statically determinate structure. So we have here a simple frame. So we have example number 2, which would be the analysis of frame. So we have this frame here. We have a beam and a column, or the horizontal member here, this is the beam, and this vertical member here, this column. And we have two supports. So on the left end we have a roller support, and on the right end we have a hinge support which is connected to our column. Okay, so we are asked to draw the shear and moment diagram and draw the qualitative deflected shape or the deflection diagram of this frame. Okay, and if you missed to watch the first part of this discussion, I posted the link in the description below, so please watch. So again, the first thing we do here is, of course, to compute the reactions. Now, at point A, we have here a roller support. That means this one is restrained vertically. So we have here, let's say, AY. And for C, we have hinge support. We have vertical and a horizontal reaction. Let's say that CY and CX respectively. Okay? So in order to compute for our reaction, then we can use the equilibrium equation. This is determinate structure. If we try to compute the number of reactions, so we have 3 reactions. We do not have a internal hinges. That means we do not have internal forces. Then we have 3 times the number of rigid member. So since we do not have internal hinge, that means we only have 1 rigid member. So we have 3 equals to 3. That means this one is statically determinate externally. Okay? But this is also a stable internally, or internally stable, since we do not have internal hinges in the beam. So this is internally stable. Okay, so we can compute the reactions by first summing up moment at C. So summing up moment at C is equal to 0. All the forces counterclockwise are positive. So we have AY times the perpendicular distance is 9 meters. Okay, so we have 4.5 plus 4.5, so we have 9 meters perpendicular distance from C. Okay, so we have 9. Then we have this one is negative since AY rotates clockwise about point C. Then we have the point load 112, and this 112 here rotates counterclockwise, therefore that is positive moment. So positive 112 times the perpendicular distance, which is 4.5 meters. Then plus the point load of 55 kilonewton. So we have 55 times the perpendicular distance 3 meters. Okay, this one. That means we have 3, and this always equals to 0. And then we have our AY here, which is equal to 74.333 kilonewton, and that is the value of our AY. Now, how about CY? Now, we can sum up forces vertical is equal to 0. All the force acting upwards are positive. So we have AY plus CY minus, we have only one external load that is acting downward, that is 112 kilonewton, and this equals to 0. We have the value of AY, which is 74.333. So we can now compute CY here, and CY is equal to 37.667 kilonewton. Now we have one unknown reactions left, and that is CX. So we can sum up forces horizontal. Now take note, CX here is not equal to 0, since we also have 55 kilonewton here, which is acting horizontally. So summation of forces horizontal is equal to 0. Forces acting to the right are positive, and that is we have negative Cx minus 55 is equal to 0. That means Cx is equal to negative 55 kilonewton. Now take note, this is negative, so therefore we have wrong assumption, and that is we have Cx acting on the opposite direction, and that is acting rightward. So we have wrong assumption, Cx direction. So that is we have Cx acting to the right, and Cx here is 55 kilonewton, while Cy is 37.667 kilonewton. Okay, so we have now the reactions, okay, on our support. So let us try now to draw the shear and moment diagram. Now again, since we have two members here which has different orientation, so we can draw the shear and moment diagram of each member individually or separately. So let's try to cut our section at point B. So we have horizontal member and vertical member. So if we cut our frame at point B, then we would have two members here with different orientation. So we have horizontal member and the vertical member of our frame. Okay, now if we cut at point B, then there would be internal forces shown at that point. Now take note, since point B here is not internal hinge, okay, so that means we have three internal forces at that point. That is, we have vertical and horizontal internal force, and we also have internal moment at that point. Okay, but for the direction of our internal force, then we assume first. Okay, so we assume first the direction of our internal forces, but if the value of that force came out to be negative, that means we have incorrect assumption. Okay, but preferably for this point, I would assume that on the vertical member of our frame, I would assume there that we have a downward internal force. Let's say that's our By. That is, since we have upward reactions at point C. So to make it in equilibrium, so we have to have a downward reaction. But again, this is a assumption. Okay, we do not know what would be the direction of our internal force. Now for the horizontal force here, we assume, or I assume here, that we have the force that is acting to the left. Let's say it's our Bx. Now for the horizontal member, so since this is at the same point, now we have the internal force here the same in magnitude with these forces here, but opposite in direction. Okay, since we have a downward By, so on the horizontal member we have upward By, and since we have a since we have a leftward Bx, then therefore we have a rightward Bx. Now we should not forget the internal moment. Now for internal moment, it is preferable to assume counterclockwise, okay, on the right side of each member, okay, on the right end of the member, since this one is, or this MB here is counterclockwise, so therefore we have MB here which is on opposite direction. That is, we have a clockwise moment at B. Okay, so again, they have the same magnitude but opposite in direction. Okay, so we can now draw the shear and moment diagram individually, but first we need to compute the value of the internal forces. So we can use equilibrium equations for each member here. So let's start, or we can use horizontal member here of our frame. So we can sum up forces vertical. So we have summation of forces vertical. All the force upwards are positive. So this equals to 0. So we have 74.33 minus 112, then plus By is equal to 0. So we have our By here, which is equal to So we have a 37.667 kilonewton. So we have the answer for By here is 37.667 kilonewton. And since we came up with a positive answer, that means our assumption that By is upward is correct. So we have the direction of our By acting upward. Okay? Now for the horizontal force of our horizontal member, we have Bx, so we have summation of force horizontal is equal to 0. All the force acting to the right are positive. Now, take note, we do not have horizontal load on horizontal member. That means our Bx here is automatically equals to 0. So we have our Bx here, 0. And our Bx here is 0 as well. And our By is the same in magnitude, so we have 37.667, but the difference is its direction. By is acting downward, whereas By on the horizontal member is acting upward. Okay? Now, for our internal moment B, so we can sum up moment at B is equal to 0. So you can use again either the vertical or horizontal member to compute for moment B. But in this case, I would be consistent with my beam. So I will use horizontal member here for our frame to compute for moment B. So we have 74.333 times the moment arm is 9. Now take note, this is negative since 74.333 here rotates clockwise, and that is against our assumption. Then plus 112, that's positive since it rotates counterclockwise, times 4.5. Then we have the moment B plus MB since that is counterclockwise, and this equals to 0. We have our moment B here is equal to 164.997 kilonewton meter. Since our answer came up positive, that means our assumption that moment B is counterclockwise is correct. So therefore, our direction or the rotation here is counterclockwise. So therefore, our moment B here is 164.997, and the same as with the moment B on the vertical member. Okay? So again, to check whether they have equal forces, then you can compute the internal force here using this vertical member here, and they should have the same answer. Okay? So since we have already computed the internal forces, okay, so we can now draw the shear and moment diagram for each member of our frame. So this one, so we can just actually use the area method, or if you have time, then you can use shear and moment equation to do the shear and moment diagram. Okay? So let's start with shear diagram. So we begin at point A. So point A here, we have 74.33 kilonewton, and that is upward. So that means we have we go up from our reference line, so that is 74.33, that is positive. Then we have 0 degree order, so we use horizontal shear here. So all the internal shear from A to this point are equal, and that is 74.33. So from this point, so we go down, we have 112 kilonewton, so our shear 0 is 74.33. This is our initial shear. Then for our second shear, we have V1 is equal to 74.333 minus the load 112. That would give us 37.667. So we go downward. And this one is negative, so we go down. That is where we have negative 37.667. So we go down here at this point. Then since we do not have a load in between 112 and By, so we have a 0 degree diagram. All the internal force here is 37.667. Now at point B, we have 37.667 as well. Then we go up, and that would give us the final shear equal to, since our final shear here is equal to negative 37.667 plus 37.667, this would give us 0. So since we end at 0 shear, therefore we have correct shear diagram. And that is our shear diagram for our beam. Now let's proceed to our moment diagram. So we do not have moment at A, since A here is a ruler support. So we begin at moment 0 is equal to 0 kilonewton meter. Okay, so we start at 0 here. Now we move to 112 kilonewton point load. Okay, so at this point, but in order to compute the moment at that point, so we compute the area of the shear diagram. So we have, let's say that's our moment 1. So we first start with a 0, then plus 74.333 times 4.5. That is the area of this load diagram here. So if you have not watched my discussion regarding how to create a shear and moment diagram, so I posted the link in the description, so please dare to watch that discussion, and that would give us equals to 334.499 kilonewton meter. Okay, so we have here 334.499 kilonewton meter, and since our shear diagram here is 0 degree, so that means we have first degree moment diagram. So we have a line. Okay, let's connect the 2 points. So we have this moment diagram here, which the value of the maximum point is 334.499. Okay, now for our final moment, let's say that's our moment 2. So we begin at 334.499, but we have negative area, this one. Okay, so we have minus 37.667 times 4.5. This would give us the moment at B equals to 164.997 kilonewton meters. Okay, so we plot at this point. So that point is 164.997, but since this is still in 0 degree, so we have a first degree line. Now our final moment, okay, let's say our M3. So we begin at 164.997. Now take note, we have internal moment at that point, and that is 164.997. Okay, and the direction of this moment is counterclockwise. According to our sign convention, if our moment is counterclockwise, that means we have a negative moment. That's our sign convention. But if our moment is rotating clockwise, that means we have a positive moment. Since we know that this one is internal moment, but in creating the moment diagram, this should serves as the external moment. Okay, for the entire beam, this one is internal moment, but for this member only, this serves as the external moment. So therefore, we should consider the sign convention for external loads. And that is again, if we have counterclockwise, that is we have negative moment, but for clockwise external moment, that is positive moment. But in this case, this one is counterclockwise, that is this one is negative. So we have a minus 164.997 this moment here, and this would give us 0. So we go down to 0 moment here. Okay, so this is 0. So that means we have correct moment diagram, since again we end at 0 moment. Okay, so this is our moment diagram. So we have now drawn the shear and moment diagram for horizontal member. Now, how about the vertical member? Okay, so let's draw the deflection diagram for the entire beam later. Okay, or for the entire structure later. Now, in our vertical member, we need to assign which side is our positive side and which side is our negative side. Now, for this one, we need to be consistent with our direction. Actually, it's up to you where you want to set as positive or negative. But for me, I would let this point or the lower point as the left side of our beam. Okay, so this one is the left and this one is the right side. So therefore, our orientation here is this one is our y-axis and this one is our x-axis. Okay, so that is our orientation. Okay, so you need to make this, or you need to adapt this orientation so that we are uniform when we draw the shear and moment diagram. Okay, so in this case, we have 55 kilonewton on the left side of our beam. So we go down. Okay, so we go to the right, to this one. That is, we have 55, or let's say it's negative 55. Then we do not have load in between 55 kilonewton load and 55 kilonewton reaction. That means we have a 0 degree at that point. Okay. So therefore, we have 55 kilonewton at this point. But take note, we have 55 kilonewton load which is acting to the left. So that means we have negative 55 plus 55, which is the load. This would give us 0. So therefore, we have 0 shear at this point. Okay. So we do not have load in between 55 and BX. So therefore, we are constant at this point. All the internal force between this point are 0. So at point B, we have 0 force here. So this would be our shear diagram. Now, for our moment diagram, now at this point, or at point C, this one is a fixed support. Therefore, we do not have moment at that point. So that means we have there 0 moment. Okay, but in case now we have moment at this point, then you need to again consider the sign convention that if the external moment is counterclockwise, then we set that as negative. So therefore, we go here or to the right of our beam, and if our moment is clockwise at this point, so we go to the left. Okay, and that is positive, since again we have this beam convention that y is on the left and x is, or the negative y is on the right side. Okay, and this one is in case we have a moment, or if we have a fixed support at point C. Okay, so we have 0 moment here, and then now take note, we have negative shear area. Take note of this one. So we have a negative moment. And then since this is in 0 degree order, so therefore our moment diagram should be in the 1st degree order. So we have moment at this point is, we start at 0 moment minus the area of the shear diagram. We have 55 times, this one is 3 meters, correct? So the area of our shear diagram is equal to negative 165 kilonewton meter. So that is negative, so therefore that is on the right region of our beam. Okay, that is because of our assumption. So again, that is a 1st degree line. Okay, so it is linear. So our load here is negative 165. Now take note, we do not have a shear area on this region here, so we go straight. Okay, so we have constant here. Since we have moment at B, which is 164.997, which is rotating clockwise, that means we have a positive moment as the sign convention. Okay, so this serves as our we adopt the sign convention for external load, even though that this one is an internal force. Okay, because this is located at the end of our support, or at the end of our member. So therefore, at this point, we have, now we begin at negative 165 plus the moment B, we have positive 164.997. This would give us approximately equal to 0. So therefore, we end at 0 moment. So that means we have correct moment diagram. Okay, so this is now the moment diagram and the shear diagram of the vertical member of our frame. Now for the deflection or qualitative deflection diagram, now take note, we have negative moment, so therefore we have a moment which is having a concave downward, or that is we have a frowning curvature. Okay, so therefore we have this curvature here, that one. Now since this one is first degree diagram or moment diagram, therefore this one is a second degree deflection diagram. Now for this side here from or in between the 55 kilonewton and point B, since we have a 0 degree moment diagram, therefore we have a first degree deflection diagram. Since we have 0 degree, that means we have a straight line here. Okay, and we have this one. Okay, so this one is a first degree deflection diagram. Now, as what you can notice here, this should be the original point B, but because of the horizontal load 55 kilonewton, there would be a movement of B, so this serves as our new B. Let's say it's our B prime. So there is a movement at this point, unless otherwise this has a support. If this has support, let's especially if this is hinge support, that means this is restricted to move horizontally. But since this is a non-rigid support, okay, or this has no external support at point B, then there would be a possibility that our point B will move either to the right or to the left side. Okay, now how about the horizontal deflection diagram? So we have now for the horizontal member, okay, so if you try to draw the qualitative deflection of our horizontal member, then we will have this one. Since we have positive moment diagram here, therefore we have a smiling bending curvature. So we have this one. We do not know yet the location of the maximum moment. And for this region here, since we have a still positive moment, then we still have a smiling curvature for deflection. So approximately this would be our deflection diagram for the horizontal member. Now if you are going to combine the deflection of the horizontal and vertical member, so we have this one. From the deflection diagram of our vertical member or our column here, now we know from point C to the point of load, 55 kilonewton, we have a frowning curvature. Okay, since frowning, since our y-axis is on the left side, okay, then that is in second degree deflection diagram. So we have this deflection diagram here. And then from 55 to point B, we have a first degree deflection diagram. So we have a line, a linear diagram here. So we have is first degree deflection diagram between point B and 55 kilonewton load. Okay, and a second degree deflection diagram between point C and the point of 55 kilonewton load. Now, as what you can see, there is a movement of our joint B here. So from this point, this is our initial point, so it moves to the left direction. So we have this new point here, we have B prime. Okay, so that is the new point or the movement of our joint B. Okay, now for the horizontal member, now looking back to the deflection diagram of our horizontal member, so this is just a horizontal, or this is just a smiling curvature. Now, however, since our point B moves, so therefore the other end of our beam also moves. So therefore, our point A moves to the left side as well. Now take note, point A here has a ruler support, or is being supported by a ruler support. So therefore, our point A is restricted only to the vertical direction. So it can move freely along the horizontal axis. Okay? So this can move freely to the left or to the right direction. So this is our new direction or new position of A. So let's say that's our A prime. But since we have a smiling curvature, so we draw the deflection of the horizontal member. So we have this as the approximation or the qualitative deflection or deflected shape of our frame. So this is now the qualitative deflected shape or the deflection diagram of our beam or our frame. Now take note, this is just approximation since we do not know yet the value or the direction of our slope, and we do not know yet the value of the vertical and horizontal deflections value. Okay? Now guys, this ends the lesson on the analysis of beam and frame. Now, if you want to be an expert on the analysis of determinate structure, you can solve or you can practice solve a lot of problems. So we have a lot of resources available online, so you can solve as many problems as you can. Okay guys, thank you for watching this video, but please don't forget to subscribe and hit the notification bell. Thank you guys, stay safe and God bless.